my God, it didn't record any audio. Yowza. Okay, y'all, so I just spent 10 minutes. I'm literally hiding in my closet from my children, trying to get this video out, and I have super run out of time, and the first time I recorded it, it didn't record any audio, so it's super frustrating. I'm going to try to give you like a very quick walkthrough. This is actually in the content library if you want to run all the way through it. Okay, so I'm trying to do number 5 from the homework, which is trace AB equals trace BA. And one of the things that I thought about when I was thinking about, like, okay, well, what does this kind of sound like? And in exercise 1, right, what we found was that if you have two operators that are the same on every basis vector of a space, then you can conclude that those operators are the same. That's what we did in exercise 1 of the homework. And I thought, wow, that kind of sounds like something that we're looking for here. If I can think of trace, if I can think of this type of trace as some kind of operator. So the first thing that we need to know is trace is a linear operator, right? If you do trace scalar, you could pull the scalars out. You do trace of a linear combination, it works out. So I'm going to let A, here come the kids, I'm going to let A be any m by n matrix, okay? And I'm going to make up an operator T1. And T1 is going to take x's from the space n by m. Right? So then when you multiply, because the operator is going to take x, it's going to take your input, it's going to right multiply it by a, and then take the trace of that square matrix. And then I've got an operator T2, and what T2 is going to do is it's going to left multiply. Yeah, hey boys, you found me. Yeah, okay, good idea. Sorry. So what I do in T2 is I left multiply that matrix X by A, and then what I'm going to do is I'm going to see are those two operators the same on all of the base vectors of this space, R n by m, and I can come up with those base vectors, because if they're the same on all of the base vectors, they're gonna be the same according to the exercise that we did in 1. Now here's the thing, when you multiply A by X, remember my input vectors, or my input matrices, are n by m, right? So when you right multiply A by X, when you right multiply, you're gonna be doing an m by n, because that's what A is, times an n by m. Those n's are gonna cancel. You're gonna be left with an m by m square matrix that you can take the trace of. Yeah, I'm going to get that for you, Jess. And then, right, if I do it the other way, if I left multiply, you're going to have an n by m, which is my source space, and an m by n. Those are going to multiply to an n by n square matrix, and again, I can calculate that trace. Okay, so I'm going to erase this because this is like a whole mess here. But basically, I want to do a really quick example because this is going to come right into place at this point, if we can wrap our heads around what it's doing. So let's take X, my source space, to be 3 by 2 matrices, and I'm going to take A, which is the matrix that I'm multiplying it by, and A can be any matrix. We're going to work that out. It's got to be 2 by 3 so that they can like make square matrices that we can take the trace of. I'm going to come up with a series of base vectors that are double indexed just so that we could like keep them straight, because all they're going to be is they're going to be zeros everywhere, except in the ith row and the jth column, they're going to be 1. So if my source space was 3 by 2 matrices, x32, which is one of my standard basis vectors, is going to have a 1 here in the third row and the second column. And let's see what happens when I do that, when I put this base vector into my operator. So I'm going to take x32 and I'm going to put it into my operator T1. Hey, please don't do that, George. Bye-bye, George. I'm gonna follow you, okay, and so what I get, right, is I'm gonna take this 2 by 3 matrix that's A, and I'm gonna right multiply it by a 3 by 2 matrix that's X. That's just one of my base vectors. And so when I do that, right, the first thing I do is I do some, great, my Amazon order ship. I take this, great. I take this to get this top left corner, right, I'm going to take the first row and the first column. That's going to give me zeros. When I take that first row and the second column's got a 1 in it, so it's going to populate this A13, and then the same thing in this to get the bottom 2 entries, and I get an A23 at the bottom. Now when I take the trace of this square matrix, it's just A23 because it's the only one along the diagonal. Now let's take a look at what's happening to x32 in my operator T2. So this is the same base vector in a different operator T2 that left multiplies. When I left multiply, I'm going to get a 3 by 3 matrix, but this first row that zeros is going to zero out that whole first row. The second row that zeros is going to zero out the whole third row. And then what's going to happen is this third row, when I multiply it out to populate my product matrix, it's going to pick up the A21 in this entry, the A22 in that entry, and the A23 in the other entry. And again, when I take the trace of that, the only diagonal element is A23. So what we've shown, and you could generalize this, that any base vector ij of your space, when you put it into T1, you get out AJI, the scalar value. When you put it into T2, you also get out AJI. And since they're the same on all of the base vectors of the space, you can calculate that by like the theorem that we did in exercise 1, they're the exact same operator. Okay, I got to roll. Thanks, guys.